Hello, this is Jennifer Martinez, and in this video we're going to talk about linear independence. Let's start with the definition. A set of vectors, v1 through vp, in Rn, is said to be linearly independent if the vector equation x1 v1 plus x2 v2 through xp vp, counting all the vectors here with weights, equals 0 has only the trivial solution. And the same set of vectors is said to be linearly dependent if there exist weights c1 through cp, not all 0, such that the same linear combination is equal to 0 with c1, c2, and cp as the weights. And when these weights are not all 0, this equation is sometimes called the linear dependence relation among these vectors. When you're checking a set of vectors to see if the set is linearly independent, and it's not, then the set is going to be linearly dependent. In other words, you can only have these two choices. And it works the other way around too. A set is linearly dependent if and only if the same set is not linearly independent. Suppose we begin with a matrix, we'll call it A, with columns as vectors. The columns are going to be A1 through AN instead of a set of vectors. The matrix equation AX equals 0, we know from past sections, can be written as a linear combination of those vectors with x1, x2, xn being the weights. And if we set it equal to 0, we know that each linear dependence relationship among the columns of A corresponds to a non-trivial solution of AX equals 0. So we have the following important fact. The columns of a matrix A are linearly independent if and only if the equation AX equals 0 has only the trivial solution. Let's look at some examples, starting with sets of 1 or 2 vectors. The first example looks at one vector. Is this one vector v equaling 1, 2 linearly independent? Well, the answer is yes. Why? Because if we look at x1v, our vector x1v equaling 0, this only has the trivial solution. V is 1, 2, which is not 0. So x1 times this vector 1, 2 can only be 0 when x is 0. It only has, again, the trivial solution. Or if you look at the matrix equation AX equals 0 and you solve that, you will see that that is, by multiplying the first row by -2 and add it to the second row, I get a row of zeros. So that means that x1 equals 0. That is the only solution. And we know that when AX equals 0 only has a trivial solution, the columns of matrix A, these columns, which is the vector, is linearly independent. So the answer was yes. So in general, a set containing only one vector, say V, is linearly independent if and only if V is not the 0 vector. So this was not the 0 vector, so it was independent. Because the equation x1v equaling 0 only has a trivial solution when V is not 0. So it is, one vector would be linearly dependent if it was the 0 vector. So if we did have the 0 vector here, you can see here x1 times 0 would have many non-trivial solutions. So a 0 vector is linearly dependent. For example, if we had the vector 0, 0, that would be linearly dependent because a number, c, times that 0 vector, c would be anything. C could be 1, 2, 3. Non-trivial. The next example will explain the nature of a linearly dependent set of 2 vectors. Example 3 from the textbook says to determine if the following set of vectors are linearly independent. So part A has the vectors v1 being 3, 1 and v2 being 6, 2. So v1 and v2 are linearly dependent because you can just multiply v1 by 2 to get to v2. Or v2 is equal to 2v1. And setting this equation equal to 0, we would get negative 2v1 plus v2 equals 0. And these are all vectors. So you can see the weights, c1 is negative 2 and c2 is 1. We found weights by definition, c1 times v1 plus c2 times v2, where the weights were non-trivial. So that shows that it's dependent. So the answer is no, it's not independent. And we can also look at ax equals 0. You could do it that way to see if there is a non-trivial solution. So here is my augmented matrix for these two vectors. And I'm going to interchange these two rows. I'm going to get a 0 in the first column of the second row here. So I'm going to multiply the first row by negative 3 and add it to the second row to get 0, 0, 0. So if we call this C1 and C2, you can see that C2 is free. So actually there's many solutions here. And C1 is equal to negative 2C2. And we just chose C2 as 1, but C2, you can add many answers. C2 could have been anything, and then just multiply by negative 2 to get the C1. So AX equals 0 also shows that there is a non-trivial solution. So it's still, the answer is no. These set of vectors are dependent, not independent. So let's look at B. We do not see that v1 is some sort of multiple of v2. So it looks like they should be independent. We know v1 and v2 are linearly independent if the equation that matches them, ax equals 0, only has the trivial solution. So for this one, I'm going to start with that. I'm going to first switch the rows. Then I'm going to divide the first row by 2. Then I'm going to get a 0 in that first column, second row, again, by multiplying the first row by negative 3 and adding it to the second. But this time we get something different. We get 0, and then we get 3 there, and a 0. So that means that x2 is 0. And if you look at the first equation, x1 must be 0 as well. So ax equals 0 only has the trivial solution. So yes, they are linearly independent. In fact, a set of any two vectors, v1 and v2, is linearly dependent if at least one of the vectors is a multiple of the other. And as we saw in example 3a, one vector was a multiple of the other. v2 was 2 times v1, so it was dependent. And if they were not a multiple of each other, then they are going to be independent. It says here that the set is linearly independent if and only if neither of the vectors is a multiple of the other. And we can easily show the second line. So what we're going to do is we're going to let C and D satisfy this equation, CV1 plus DV2 equaling 0, where V1 is not a multiple of V2. If C does not equal 0, then V1 is negative V2 over C, just solving for V1. But this is impossible. That would mean V1 is indeed a multiple of V2. So C must be 0. And you can actually find that D must also be 0 by saying V2 cannot be a multiple of V1 and do the same argument. So similarly, D needs to be 0 as well. Therefore, it only has the trivial solution, and it is indeed independent. So what we proved here is if you had P if and only if Q, or P, I'll write it like this. We proved here if neither vector is a multiple of the other, then it's linearly independent. So we actually did Q implies P. If we wanted to do this the other way around, meaning conversely, let V1, V2 be linearly independent, would be P implies Q. We want to show that neither the vectors can be a multiple of the other. So I'm going to do is I'm going to suppose V1 is a multiple of V2, or V1 equals some K times V2, where K is not equal to 0. And then I can just subtract over that KV2 and get this line. V1 minus KV2 equals 0. That means that there would be weights, C1 being 1 and C2 being negative K, where that linear combination has a non-trivial solution, where C1 V1 plus C2 V2 equals 0. It would mean that V1 and V2 are dependent, which is not the case. So therefore, V1 cannot be a multiple of the other. So now let's look at a set of 2 or more vectors. So what if you have more than 2 vectors? Example 1 is an example where we have 3 vectors, and it says determine if the set is linearly independent. You can see 1 is not a multiple of each other. So does that mean that they're always independent? Well, let's check it out. We know if V1, V2, V3 are linearly independent, then the matrix only has the trivial solution. So let's go ahead and look at that augmented matrix. And again, let's reduce that to echelon form, multiplying the first row by -2 and adding it to the second by getting 0, -3, -3, and 0. Doing the same thing, multiplying the first row by -3 and adding it to the third, we get 0, -6, and -6, 0. Then, we could just multiply the second row by -2 and add it to the third, and we're going to get a row of zeros. And we can stop here because we know that x3 is free. Solving the second equation for x2, you would get x2 equals -x3 just by dividing everything by -3 and then bringing over that x3. And then from the first row, we know x1 equals -4x2 minus 2x3. And I could have row reduced this and got this firsthand, but since this is pretty quick here, I'm just going to say that this is equal to -x3. And then you can see here that x1 is equal just to x3, because that would be +4. So it has many solutions that are non-trivial. So determine if the set is linearly independent. No, it's not. It's dependent. So you can see here, it's not quite so clear. A V1 does not look like a multiple of V2. None of them look like a multiple of each other, yet they were dependent. Part B asks, if possible, to find a linear dependence relation among the 3 vectors, which is our linear combination with weights x1, x2, and x3. So since there's many answers here, I'm just going to pick anything for x3, maybe 1. So therefore, x2 would be -1, x1 would be 2, and we'd have our relation 2v1 minus v2 plus v3 equals 0. What about this example? Is this independent? This would be yes, since this matrix here only has a trivial solution.